Okay, I'm Eric Admin, President of the Sno-King Watershed Council, and this evening's class is water chemistry monitoring. Sno-King Watershed Council is an all-volunteer nonprofit organization, and our mission is to help people protect local creeks and natural areas. We are part of Global Water Watch, which is a larger international organization, and they're headquartered out of Auburn University in Alabama. And that's where we get our training materials from. They also have a kind of a sister program, Alabama Water Watch. And so some of the training videos that we're going to be watching this evening are from Alabama Water Watch, which also uses the same techniques. So what we're going to go through this evening, just briefly touch on again, kind of the reasons behind water monitoring, talk about briefly some basic concepts about watersheds and water pollution, and then going to spend the bulk of the class on learning Global Water Watch techniques for physical and chemical water monitoring. So water monitoring, again, is a regular systematic assessment of conditions in a water body by taking measurements. People do it for a variety of reasons. They could do it for regulatory reasons. They could do it because they want to understand what's happening in their watershed. They might do it because they want to educate others. It's done by government agencies and nonprofits. It's done by school groups. It's done by individual citizens. It's usually done on streams, rivers, lakes, and other water bodies. And this evening, we're going to talk about the how of water chemistry monitoring. Just to review some basic concepts, we covered the concept of a watershed, and that's important because it's an area of land that drains to a stream or a larger water body. And everything that happens in that watershed, everything that falls on the ground in that watershed ends up in that water and has a significant effect on that water. We also talked about stormwater in particular. That's water that falls from the sky and runs off the land. And that's got some issues. One of them is that it ends up in local creeks after it goes through storm drains. In an urban setting, you have a lot higher percentage of runoff and it has a lot more pollutants. So that's concerning to us. And it can have things including tire particles, chemicals, a host of different things that can affect the health of what lives in the stream. It also, just in terms of its sheer volume, has an impact on streams because it tends to flow off in high volume. We mentioned in our previous classes some of the different things that people can do themselves to reduce water pollution. So that includes things like rain gardens, restoring stream buffers, picking up pet waste, fixing leaky vehicles, avoiding use of chemicals, using green infrastructure techniques like green roofs and porous pavement. So those are some of the things that people can do themselves. Okay, we're going to jump right into water chemistry monitoring. And so these are some of the variables that are commonly monitored. This is something that's called the Water Quality Index. It was produced by the Department of Ecology to give an overall index for water quality in a given water body. And we don't measure all these variables in our Global Water Watch technique, but we measure several of these variables. And these variables, we'll talk about them individually as to why they're important for water quality, but these are all variables that are important for water quality. There's different ways that you can collect water data. So one is with an electronic meter. With a probe that you put in a stream, and they have pluses and minuses. Another would be you can collect a sample and you can take it back to a laboratory. You can also have something that has a fixed position in a stream and measures certain variables like maybe turbidity and flow or temperature, various other things. You can have essentially like a data logger, or you can have the setup that we're using, which is a small test kit and some other small pieces of equipment, and take that out to the field. And we'll talk about what the pluses and minuses are of those different techniques. So with an electronic meter, what it consists of is You've got a handheld unit, which is like a controller, a computer. You have a probe, a sensor probe that you put into the water body, and it gives you relatively instantaneous results. The downside to it is that they're expensive. They typically cost thousands of dollars a piece. They need somebody who really understands them well to calibrate them. They need calibration fluids. There's an annual cost associated with them as well. But they are great because they can measure a lot of different variables and they can do it very quickly. So some of the programs that we work with use these, and we have one of these meters in our program, but we don't use it for all of our monitoring sites. Another example of something that can be used is, this is a piece of equipment we have called a photometer, where we collect a sample, bring it back, and then we mix a reagent with the water and put it in this photometer, and it gives us a very precise measurement of certain variables that we can't measure in other ways, such as phosphate and copper, a couple of the reagents that we have. This is a look at the equipment that we use in our Global Water Watch monitoring. And so what you see on the left there is a Lamont test kit. So it's just a little portable kit that has a variety of what we refer to as reagents. They're essentially chemicals that you use to do some reactions. And the result of those reactions gives you some information about what's going on in the water body. So it's basically a variety of reagents and a few pieces of equipment, different types of bottles and test tubes. And then there's some other peripheral equipment that we use just to, for instance, what we call control water. So just some tap water that we can use for a control in our turbidity test, and a few other odds and ends like instructions. But that's basically the setup that we use for our Global Water Watch monitoring. The things that we monitor in this particular technique are the variables that are listed here: temperature, air and water, pH, dissolved oxygen, alkalinity, hardness, and turbidity. And as we go through the presentation here, we'll talk about each of those variables in turn. There are some basic principles you need to follow when doing water chemistry monitoring, and we'll talk about those first. The first one is just simply to have a set of written directions with you and read and follow the steps carefully. If you forget a test or forget a step, your test will not turn out correctly. And so one of the basic first principles to keep in mind is, even if you've done this a number of times, remember to follow the directions. Another is, I mentioned that we use these things which are called reagents, and they have expiration dates, which are typically about a year or so. Those are printed on the bottle, and then we additionally typically mark them on the bottle so it's easier to read, because the printing may rub off or it's small, difficult to read. So before we go out and monitor, we go through the kit and we verify that all the different reagents we have in the kit are not expired. A couple of other general principles are, when you record your data on the data sheet, try to make it readable in case you want to refer to it in the future or you're going to send it to somebody. And then try to enter it in a timely manner so that somebody can actually look at your data and something happens with it. Another general principle is we try to make sure that we properly dispose of waste and expired chemicals. And so what we do with those, they're not actually generally super hazardous, but as a best practice, we collect them in a waste container. And then when we come back from monitoring, we'll just put those down the drain where they go into the sanitary sewer. So at least they're diluted and somewhat treated before they would make it back out into the water system. And the main general principle that we follow is that having no information is better than having the wrong information. So when in doubt, if you think you may have not done a step correctly, do it over again. A few more general tips. One is that you can help use that kit can be used to organize things while you're doing your testing. So for instance, you may have a half-filled test tube full of a solution, and if you set it on the edge of a table or the edge of this blue box or something, you may knock it over. So it just helps to keep things organized. You can actually just work out of the kit and keep things in there while you're monitoring. Another principle is that there's this thing called a meniscus. So if you fill a tube of water and you look at it from the side, you'll notice that there's a little bit of a curvature to the water. And that's due to surface tension as it moves up the side of that vessel. So what we're looking for is we want the bottom of the meniscus to be even with the measuring line. So that's when they say fill it to the 10 parts per million line, that's a technique, or that's what you're looking for, is to be filled to that point. We'll show you a technique you'll see when dispensing with drops from a bottle, but essentially you want to hold it right side up, squeeze it, turn it upside down, and then release it, and it'll suck back in a little bit of air. And that way you don't accidentally run a bunch of drops out at once. So that's a technique you'll practice, and it'll come easily to you after a couple times. Another general concept about monitoring is this concept of a titration reaction and a titration endpoint. So titration reaction is where we've added some reagents to the water, which cause it to turn a certain color. And then we'll add a different reagent to that water, and we'll add it a drop at a time. And we're looking for a color change. And ultimately, we're looking for the point where there is no more color change. So we've added a drop, added a drop, added a drop. We keep getting color change. Now we add one more drop. There's no more color change. So we don't count that very last drop that was added. So your titration endpoint is when you have no more color change. Okay, now we're going to talk about the specific different tests that we do. So we'll talk about the principles of each of these tests, and then we'll talk about the practice of how you do the test. So with regard to temperature, temperature is important because it affects the properties of the water. One of the ways in which it does this is that cold water holds more dissolved oxygen. So you'll find that your dissolved oxygen numbers are higher typically in the wintertime when the water's colder. And as far as cold water holding more dissolved oxygen, another reason why that's important is that, for instance, in the summertime, some of the local water bodies can get too warm, and also their dissolved oxygen get too low, and they can cause a barrier for salmon migration. It also affects feeding, reproduction, and metabolism. In particular, some of our local, what we call salmonids, salmon, trout, and steelhead, need very cold water. That's what they're adapted to. So if we have warm water, it can be a problem. And this is set up, there's a standard in Washington state law that basically lays out what the guidelines are for different temperatures that you want to find for different types of salmonid habitat and activities. In terms of the practice, we just use this armored thermometer. It's just an alcohol-based thermometer. So a couple of general principles: you want to hold it by the eyelet, which is where that string goes through it, not the bulb, when you're reading the temperature, because if your fingers are on the bottom part, which we call the bulb, then you could affect the temperature. And if you're just using one thermometer, we recommend you measure air, then water, just so you don't get any effect of evaporative cooling. We're going to record the temperature that we see in Celsius, and with the thermometers that we use, the most accurate that you can get is to the nearest half a unit. So either 7 degrees or 7.5, that's as close as you're going to get. Okay, I mentioned we're going to watch some instructional videos. And so right now we're going to watch the Alabama Water Watch video on air and water temperature.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for taking air and water temperatures. Before arriving at the site, make sure there are no separations or breaks in the thermometer's alcohol column. If there is a break, your readings will be inaccurate. We will start with air temperature. Always take air temperature before water temperature for the most accurate readings. Upon arrival at the site, place the dry thermometer in the shade until the temperature stabilizes. This will usually take 2 to 3 minutes. Once the temperature stabilizes, hold the thermometer by the eyelet to avoid touching the bulb. Read and record the temperature to the nearest ½ degree Celsius on your data form. For water temperature, submerge the thermometer in the water until the temperature stabilizes, or about 2 to 3 minutes. It may be necessary to anchor the thermometer to prevent loss in strong currents, cloudy water, or deep water. This can be done by tying a cord through the eyelet and attaching it to a stable object. When the temperature stabilizes, read the thermometer while it is still submerged, or immediately after removing it from the water. Record the temperature to the nearest ½ degree Celsius on your data form. Thanks for watching. If you have any comments or questions, give us a shout.
Okay, so that was air and water temperatures. That's pretty straightforward. So the next measurement that we're going to talk about is pH. So pH is essentially acid and base, and it's a scale from 0 to 14. 7 is considered neutral. Most living creatures like to live pretty close to 7. And the optimum for fish is between 6 to 8.5. The chart there gives you some example of the pH of some different things. To measure pH, we use one of the tubes in the Lamont kit. It's kind of this tall, skinny tube. We're going to rinse that tube 3 times with sample water and then fill it to the 10 milliliter line, which is close to the top. Then we're going to add 10 drops of what's called wide range indicator. And then you put the lid on, turn it upside down a few times to mix it thoroughly. Make sure it's thoroughly mixed. And then you'll put it into a color comparator and try to find the closest color. So that's basically the steps of doing pH. So we're going to take a look at the Alabama Water Watch instructional video on pH.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for measuring pH with 2 different Lamont testing kits, one from before and after 2013. For this test, you will need the wide range indicator, the small tube with cap, and the color comparators. Remove the small tube from your kit and rinse 2 to 3 times with water from your site. Fill the tube above the line with site water and flick out excess until the bottom of the meniscus touches the 5 milliliter line. This is your sample. Locate the wide range indicator bottle in your kit. Add 10 drops to your sample. When dispensing the reagent, take care to hold the dropper bottle vertically. This ensures uniform size drops. Tap the tube and invert 2 to 3 times to mix. The color will be pastel or pale. Insert the tube into the color comparator and match the sample to a color. It is helpful to hold the color comparator up to a well-lit uniform background like a clear patch of sky. Record the pH to the nearest half unit. For this test, you will need the wide range indicator, small plastic tube with cap, and the OctaSlide viewer with both OctaSlide color bars. Remove the small plastic tube from your kit and rinse 2 to 3 times with water from your site. Fill the tube above the line with site water and flick out excess until the bottom of the meniscus touches the 10 milliliter line. This is your sample. Locate the wide range indicator bottle in your kit. Add 10 drops to your sample. When dispensing the reagent, take care to hold the dropper bottle vertically. This ensures uniform size drops. Cap and invert the tube 2 to 3 times to mix. The color will be pastel or pale. Insert the tube into the OctaSlide viewer and match the color of the water. It is helpful to hold the viewer up to a well-lit uniform background, such as a clear patch of sky. You may need to change the OctaSlide color bar to find the best match. Record the pH to the nearest half unit. Thanks for watching. If you have any comments or questions, give us a shout.
Just a quick question. I just want to check in. Do those videos look okay to you guys? Or do they look a little, are they stopping and starting?
They're working perfect for me.
Okay.
Yeah, a little jerky, but it's easy to follow.
Are you hitting those check marks for optimizing for a video clip when you share the video?
That's what I was just looking for.
Also, I gotta say that's one of the better stock music tracks to put to an educational video.
Okay. Actually, I'm not seeing that option right now on the share. So
There are 2 little check boxes at the bottom of the window for me, but I don't know if you're on a Windows machine if it would look different.
okay, well, I'll get back. I'll share again. Oh, here we go. There it is. Optimized video clip. Okay, we'll make sure that works better for the next one. And give me some feedback if it's working okay. Okay, so that was pH. So the next test we're going to talk about is hardness. And hardness is essentially, we're talking about mineral content of the water, primarily calcium and magnesium ions. And these are necessary for things that live in the water. And what sort of determines the hardness is the fundamental mineral content of the land that you're in. So if you're in an area that's got a lot of like limestone and sandstone type rock, you tend to have higher hardness. Our area, we tend to not have super high hardness. But you also can find a correlation between hardness depending on if you normally find a certain level and you have high amount of stormwater, you may find that your level of hardness drops because the water is basically more diluted. So it's also a little bit of a proxy for how much dilution is happening in the watershed as well. So there's a table of some representative values of hardness. And I would say that the water that we have around here would be kind of in the middle range typically. And we're gonna switch over to watch a video on how to do hardness.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for determining water hardness. If you are testing in coastal waters, be sure to conduct a salinity test first. If salinity is detected, do not perform the hardness test. For this test, you will need the hardness tube, hardness reagent number 5, hardness reagent number 6 tablets, and hardness reagent number 7. Remove the hardness tube from your kit. Rinse the tube 2 to 3 times with water from your site. Fill the tube above the line with site water and flick out excess until the bottom of the meniscus touches the line. This is your 10 parts per million sample. Locate the hardness reagent number 5 bottle. Add 5 drops to your sample and mix. When dispensing the reagent, take care to hold the dropper bottle vertically. This ensures uniform size drops. Locate the hardness reagent number 6 tablet bottle. This reagent is in tablet form and is very soluble. Take extra care to not touch the tablet or allow any water to enter the tablet bottle. Using the cap of the bottle, dispense a single tablet into the water sample. Cap and shake the tube until the tablet dissolves. A pink color will develop. If a blue color develops, there is no measurable hardness and the value should be recorded as 0 milligrams per liter. Locate the hardness reagent number 7 bottle. Add 1 drop of reagent at a time, swirling to mix between each. Be sure to allow time between drops for color change to occur, especially during cold weather. You will need to know how many drops you add to your sample, so don't forget to count. Continue adding single drops of the reagent until the pink color changes to blue and eventually no longer changes with any addition. Do not count the last drop if there is no color change after its addition. Multiply the number of drops added by 10 to calculate the hardness value in milligrams per liter. Thanks for watching. If you have any comments or questions, give us a shout.
Okay, does anybody have any questions about hardness? Okay, so moving on, the next test that's kind of related to hardness is alkalinity. And alkalinity and hardness typically have kind of a relationship because they're sort of different sides of the same coin. But alkalinity is a measure of the buffering capacity of water. So what that means is how resistant is that water to changes in pH when you add something to it that would affect the pH. So if you have a higher alkalinity, it's more resistant to changes in pH. But too high of an alkalinity could be a problem as well. And there's a couple of particular ions that are a source of alkalinity. And so you can see that if you have like calcium carbonate, the calcium gives you the hardness and the carbonate gives you the alkalinity. So these are some of the ranges that we typically would find for alkalinity. And again, in our area, we're typically kind of right in the middle on alkalinity. Alkalinity is a pretty similar test to hardness. It's another titration-based test. So we'll watch a quick video on how to test for alkalinity.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for measuring alkalinity. For this test, you will need the alkalinity test tube, BCG MR tablets, alkalinity titration reagent B, and a plastic dropper with no line. Remove the alkalinity test tube from your kit. Rinse the tube 2 to 3 times with water from your site. Fill the tube above the 10 milliliter line with site water and flick out excess until the bottom of the meniscus touches the 10 milliliter line. Locate the BCG MR tablet bottle. This reagent is in tablet form and is very soluble. Take extra care to not touch the tablet or allow any water to enter the tablet bottle. Use the cap of the tablet bottle and dispense a single tablet into the water sample. Cap and shake the tube until the tablet dissolves. A blue-green color will develop. If a pink or pink-gray color develops, there is no measurable alkalinity and the value should be recorded as 0 milligrams per liter. Locate the plastic dropper with the orange or black bulb. Also, locate alkalinity titration reagent B. Fill the dropper with the reagent. Hold the dropper vertically and add 1 drop at a time to the water sample in the tube. Swirl to mix between each drop. Be sure to allow time between drops for color change to occur, especially during cold weather. You will need to know how many drops you add to your sample, so don't forget to count. Continue adding single drops of the reagent until the blue-green color changes to pink and eventually no longer changes with any addition. Do not count the last drop when there is no color change after its addition. Refill the dropper when needed to ensure uniform size drops. Multiply the number of drops added by 5 to calculate a total alkalinity value in milligrams per liter. Thanks for watching. If you have any comments or questions, give us a shout.
Okay, that was the alkalinity test. Anybody have any questions about the alkalinity test? Pretty straightforward test. Just a couple things to add about those tests. One is they showed a technique called flicking, which is something that you'll discover. It's just an easy way to just get a little bit of water out of the test tube because if you try to pour it out sideways, you'll get more out than you want. And it's just an easy way to drop a little bit out, to drop your level down a little bit. And the other thing is that those tablets now come in, since those videos were made, they've repackaged the tablets. So they come in blister packs, not bottles. So you don't have to worry so much about getting water in your bottle of tablets. But those are just a couple of minor things. Otherwise, those are still pretty current. Okay, the next thing that we're going to talk about is what's called turbidity. So in terms of principles, turbidity is a measure of how clear the water is. And there's different things that can cause increased turbidity. Usually it's some form of dirt, but it can be things running off of roads or construction sites or just banks of streams eroding. It can be a variety of different things that can lead to increased turbidity. Normally around here, you'll find most streams have very low to 0 turbidity most of the time. But when it rains in an urban stream in particular, the turbidity will increase quite a bit and you could see a really cloudy stream. If you're out in somewhere that doesn't have like a glacier running into it, but you're out in a stream in more of a wilderness area, typically you would see very little change in turbidity even in a rainstorm. This photograph is an example of the stream that I live on called Little Swamp Creek, where we saw a very high turbidity and traced it upstream to a construction site. Some of the issues with turbidity is it can cause direct harm to fish and other aquatic life, and it can also bury the gravel beds, the redds that salmon need. And another aspect of turbidity is that the dirt particles that are traveling in the water provide attachment points for other pollutants, including heavy metals and bacteria. So there's a couple different types of tests that we do and a couple different units of measurement. So the Lamont kits come with these JTU turbidity tubes, and that is, you'll never need to know this unless it's like a crossword puzzle, but Jackson turbidity units are JTUs. And so that's one measure of turbidity, which is really kind of more of a historic measurement, but it's what's used in the Global Water Watch kits. Then there's another unit, which is referred to as NTUs. The full name is nephelometric turbidity units, but everybody just says NTUs. And NTUs are something that is used more by regulatory agencies. So if you wanted to communicate with the Department of Ecology and you said, hey, I found high turbidity and it was 100 JTUs, they might scratch their head and look confused. But if you said it was 100 NTUs over background, then they would go, oh, that's a problem. So we've augmented our Lamont kits with these turbidity tubes, and I'll show you how we use those as we go through the presentation here. So to do the Lamont kit test for turbidity, you use these two tubes that come in the kit, and you typically label one control, one sample. So sample is the water you're going to collect out of the stream. Control, you're going to put tap water in or bottled water. You're going to fill it up to 50 milliliter mark, your sample water. Then you're going to do the same with your control. And you're looking down through the tops of these tubes to see there's a little dot in the bottom, and which dot looks more fuzzy or opaque. And if they both look the same, then you know that you have relatively little turbidity, but what you'll do is you'll still add an addition of this turbidity reagent to the control, and you're essentially going to keep adding it until it becomes more cloudy than the sample, and you won't count that last addition when you record your additions. So that's an example of the turbidity reagent being drawn up, added to the two different, added to the control water, and then looking down, and you can see that now it's more opaque or fuzzy. So we're going to watch a quick video on how to do that particular test for turbidity using the Lamont kit.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for determining the turbidity of a water body. For this test, you will need turbidity columns, standard turbidity reagent, stirring rod, and bottled distilled or tap water. Locate the turbidity columns in your kit. Fill one column to the 50 milliliter line with sample water. Look down through the column and locate the black dot on the bottom. If the dot is not visible, empty and refill the column to the 25 milliliter line. If the dot is still not visible, record turbidity as too high to measure, or THTM, in the comments section of your data form. Fill the second turbidity column with an equal amount of bottled distilled or tap water. This is your control column. It may be helpful to label one of the turbidity columns as sample and the other as control to avoid confusion. Place the columns side by side on a firm level surface and look down through them to compare the clarity or fuzziness of the black dots. Do not consider watercolor. Locate the standard turbidity reagent. Shake the bottle vigorously, then add half a milliliter of the reagent to the control column. Mix the contents of both columns with a stirring rod, tapping the rod to remove excess water between stirrings. Place the two columns side by side on a firm level surface and look down through them to compare the clarity or fuzziness of the black dots. Remember not to consider watercolor. If the control dot is less fuzzy than the sample, add half a milliliter of turbidity reagent at a time to the control column. Between each addition, stir the contents of both columns and vigorously shake the turbidity reagent bottle. You will need to know how many additions you add to the control column, so don't forget to count. Once the control dot is fuzzier than the sample, record the number of additions, not counting the last addition. For example, if just one addition of turbidity reagent makes the control column dot fuzzier than the sample column dot, record as 0 additions. In this case, 3 additions of turbidity reagent made the control column dot fuzzier than the sample column dot, so we would record it as 2 additions. Use the number of measured additions of turbidity reagent to find the corresponding turbidity value on the chart in your water chemistry manual. Be sure to read the column on the chart corresponding to the original sample volume of either 50 milliliters or 25 milliliters. Thanks for watching. If you have any comments or questions, give us a shout.
So just one thing to add on the turbidity test is that they mentioned consulting the table in your manual, and the data sheet has the calculation built right into it. So when you record your addition, it will tell you how to multiply it out based on the sample size that you used. Okay, so that was turbidity with the Global Water Watch kit. There's also the tubes that we use, and there's a couple different ones that we have. There's one that has a chart on it. And so the way that you use this tube or to calculate turbidity is, first of all, you want to gather a sample of water. It's helpful to gather it in a separate container, and then you can pour it into the tube because you're trying to fill this tube up. And the tube is pretty tall, so unless your water is a little bit deep, it could be difficult to fill it all the way to the top without a separate container. So then you're going to pour the water into the tube basically until the tube is full, or until you cannot see that Secchi disc on the bottom. That little black and white disc is referred to as a Secchi disc. They also make larger versions of these that you would lower on a rope, like into a lake or a larger water body to measure the clarity of the water there and measure how far you lower it until you can't see it. In this case, we're using a tube, and you're looking down through the top of the tube, and you either pour water in until you can't see it anymore, or you fill it and release water until you can just barely see it. And then when you just barely see it, you note on this particular one, you note how high it is, how deep that water is in centimeters in that tube. And there's a standard relationship between depth of water and turbidity that is expressed in this chart. So if you have a given number of centimeters on the tube, then you consult the chart and it gives you the turbidity in NTUs. And you'll record that in a space on the data sheet for other observations. The other type of tube that we have is a very similar tube. The only difference is that this tube, instead of using a centimeter reading, what it has NTUs directly marked on the side of the tube. So you can just look at let the water out until you can just barely see that Secchi disc. And then you can note the NTUs directly on the side of the tube. So that's the difference. So there's a couple different ways that we do turbidity. Okay, we're going to move on to our next test, which is dissolved oxygen. And this is really seemingly the most complicated test. Once you've done it a few times, then you get a little bit quicker at doing it. So for instance, my wife and I will monitor together, and we'll do this whole set of tests in about 15 to 20 minutes. But initially, when you're walking through it, it takes you a little while because you want to make sure each step takes you a little bit longer when you're newer at it. So the dissolved oxygen test, why is dissolved oxygen important? It's because things that live in the water need oxygen to survive. And there's a couple different ways it gets in there. One is just simple aeration of the water. So like water going over a waterfall, something like that. And the other is released by plants during photosynthesis. And then you can also have oxygen disappear from water when you have things like plants that are rotting and decomposing, breaking down, or other things that are decomposing. So there's different ways that the dissolved oxygen level can go up and down. And another principle that we talked about is temperature affects it as well. Different things that live in the water, in particular fish and other and salmonids in our area, need different levels of dissolved oxygen. So like in the South, say in Alabama, they have some warmer, slower moving water, and they've got things that are adapted, like catfish, for instance, can tolerate pretty low dissolved oxygen. Whereas in our area, we've got salmon and trout, and they need a lot higher dissolved oxygen. So we're usually looking for it in that greater than 8 range, typically in our area. I mentioned that dissolved oxygen and temperature have a relationship. So the colder the water, the more dissolved oxygen it can hold, and the warmer the water, the less dissolved oxygen. So we'll just walk quickly through the steps, and then we'll watch a video where they put it all together. So the first part is collecting the sample. So there's 2 bottles that are used to collect the sample. And when you do this test, you do it with, basically you collect 2 samples and you repeat your test. So you're essentially double checking yourself, and your end result has to be within 0.6 parts per million of dissolved oxygen, or else you have to repeat the test. So step 1 is you collect your sample. So you basically just rinse those bottles a few times and then submerge them, and then cap them underwater and make sure there's no bubbles in them. And that's the collecting the sample portion. Then you'll add a series of reagents in what's called fixing the sample. And so then the final part that you're going to do once you have the sample fixed is you're going to do what's called titrating the sample, where you use some additional reagents and go through a process to come up with what are the parts per million of dissolved oxygen, or milligrams per liter. And so these are just some shots of the different component parts, which we'll go through in the video. One of the things to look at is how you read that little, they call it a direct reading titrator. It looks like a little syringe. And the way that you read it is like that one's reading right at 0. That flat part is where you read the measurement on a syringe. So this is kind of titrating the sample and what you'll see in terms of color change. And when you're all done, you're looking for it to end up as clear. And then you're done with that titration reaction. So we're going to switch over and watch part 1 of dissolved oxygen.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for collecting and fixing a sample used to determine the dissolved oxygen in water. This video corresponds to Step A and Step B in the Water Chemistry Manual. There is a separate video for Step C, titrating the sample. For this step, you will need the 2 water sampling bottles from your kit. 2 replicate samples for dissolved oxygen must be taken to ensure precision. Replicates are 2 samples collected at the same time and place. You will use both water sample bottles in your kit. Uncap the bottles and rinse 2 to 3 times with water from your site. To fill the bottles, hold them upside down in the same hand and submerge them below the surface of the water. Avoid disturbing the bottom of the stream. Allow the sample bottles to fill while completely underwater. Move or shake the bottles to allow all air bubbles to escape. Invert caps and cap the bottles upside down while they are still submerged. Remove the capped bottles from the water and invert them to make sure no air bubbles are trapped inside. If air bubbles are present, even if they are only in one bottle, empty both sample bottles and refill them with water again. Once a satisfactory sample has been collected, proceed immediately with the next steps. For this step you will need manganese sulfate, alkaline potassium iodide azide, and 1:1 sulfuric acid. Each of the following steps should be done for both samples collected in step A, one after the other. Some of the reagents used for this step are hazardous. Children using these chemicals should be carefully supervised. Make yourself aware of and adhere to the recommended Alabama Water Watch safety protocols. Also remember to hold reagent bottles vertically to ensure uniform size drops. Locate the manganese sulfate bottle. Uncap your samples and add 8 drops of reagent to each. Locate the alkaline potassium iodide azide bottle and add 8 drops to each sample. Cap the bottles and rinse the outsides to remove traces of reagents that the bottles may have come in contact with. Mix the bottles by inverting at least 10 times. At this point, a tan, cloudy precipitate will form. Allow the precipitate to settle below the shoulder of the bottles. This may take a few minutes. Locate the 1:1 sulfuric acid bottle. Add 8 drops to each sample. Cap bottles and rinse the outside. At this point, the sample will contain dark brown flecks. Repeatedly invert the sample bottles to mix until most of the flecks have dissolved. Be patient during this step. Brown flecks in DO bottles may take several minutes to dissolve, especially in cold water. It may be helpful to begin sampling your site with the dissolved oxygen test so that other tests may be performed while waiting for DO reactions to complete. Your final sample should resemble apple juice or tea. At this point, your samples are now fixed. This means the oxygen in the sample is chemically trapped and that contact between the water sample and the atmosphere will not affect the test result. Please watch the second dissolved oxygen instructional video to see the proper method for titrating your samples. Thanks for watching. If you have any comments or questions, give us a shout.
Okay, and we're going to watch the second video right now.
Alabama Water Watch instructional video series. This video will show the proper method for titrating water samples that have already been fixed for the dissolved oxygen test. This video corresponds with Step C in the Water Chemistry Manual. There is a separate video for Steps A and B, collecting and fixing the sample. For this step, you will need a titration tube, starch indicator, sodium thiosulfate, and the direct reading titrator. This entire process should be completed for one sample before starting the second sample. Locate the titration tube in your kit. Rinse the tube 2 to 3 times with a small amount of the fixed sample from the first water sampling bottle. Waste can be put in a waste container or broadcasted in a vegetated area. Fill the titration tube to the 20 milliliter line with the same fixed sample. Locate the starch indicator in your kit. Add 8 drops to the tube and gently swirl to mix. The sample should turn dark blue to black.
Cap the titration tube with the corresponding cap. It should have a hole in the center. Locate the direct reading titrator and the sodium thiosulfate bottle in your kit. Depress the plunger on the titrator and insert into the hole in the top of the sodium thiosulfate bottle. Invert both the bottle and the titrator. Pull the plunger on the titrator until the large ring on the plunger is opposite the 0 line on the scale. Make sure there are no air bubbles in the titrator. Bubbles may be removed by moving the plunger up and down while the bottle of sodium thiosulfate is inverted. Insert the filled titrator into the center hole of the titration tube cap. Add 1 drop at a time from the titrator, gently swirling the tube between drops. You do not need to count the drops for this test. Continue adding 1 drop at a time until the dark solution turns clear. During the titration, if the plunger tip reaches the bottom line on the titrator scale before the solution is clear, refill the titrator to the 0 line with sodium thiosulfate and continue the titration. If you have to refill, be sure to add 10 parts per million to your second parts per million value and record the total value required for the titration. Hold the tube against a white background to be sure that the solution is clear and not faint blue. Read the number on the titrator where the widest part of the plunger meets the line on the scale. Each minor division on the titrator scale equals 0.2 parts per million. Record the value to the nearest 0.2 parts per million. Repeat these steps for the second sample bottle. If the two DO results are not within 0.6 parts per million of each other, season and refill the titration tube with leftover fixed sample from the first sample bottle and follow the titration steps. If the results still vary by more than 0.6 parts per million, repeat the entire procedure with new samples of water from the site. Leftover sodium thiosulfate in the titrator could have been contaminated with the water sample and should be discarded. Do not return the leftover titrant to the bottle. Thanks for watching. If you have any comments or questions, give us a shout. Welcome to the Alabama Water Watch instructional video series.
Okay, does anybody have any questions about dissolved oxygen?
It's just getting a little more complicated.
It is. But you'll have a chance to practice it, and it's once you've done it a few times, then the steps are easier to remember. But initially, it does seem like kind of a complicated test.
I was just wondering how the depth of the water that you take the sample from matters in any of these samples that we take. They don't really go into that when they measure in these videos.
Yeah, that's a good point. Temperature and pressure, those different factors could affect the results. Mostly, though, we're just sampling near the surface. So, our samples are just surface samples, so I don't know how it would affect it. So, good question.
Okay. Well, I was thinking, though, that you would probably want to do it pretty close to the surface, because if your stream varies through the seasons and you had started out taking them all at a foot deep, and then in the summer you don't have a foot of water, then it might affect your readings, I would think.
Yeah, that's a good point as well.
Yeah.
So you definitely want to try to be consistent in how you do it throughout the year.
Mm-hmm. Okay.
Okay, we're just about done here. There's just a little bit more to go through, and then we'll talk about what comes next. So once you've done those tests, then the next thing that you do is calculate what's called dissolved oxygen saturation. And that's essentially at a given temperature, elevation, and salinity. We don't really control for elevation and salinity, but essentially at a given temperature, how much dissolved oxygen would we expect to find? What would be the maximum? What would be 100% saturated? And then compare what you have. So if you come up with a number, let's say that your temperature was 10, and on the left-hand column, the 100% saturated at 10 degrees Celsius would be 11.27 milligrams per liter or parts per million. If you came up with a number of 10, or say 9, you divide 9 by 11.7 to come up with your percentage dissolved oxygen saturation. And usually that would only be a concern if you, for some reason, it's possible you can have supersaturated conditions, which you might find that at like the base of a dam or someplace where there's massive amount of aeration. But that's kind of the end of this measurement, is dissolved oxygen saturation. It does have some implications. So depending on what type of numbers you find, typically we're finding between 80 to 100. So those are usually pretty good numbers locally. But if you found something way outside that, it could have some implications. So with each of these tests, as you go along, you want to record it on your data sheet, and the data sheet looks like this. And then the next step would be enter it into the database. And then at that point, you are done with your physical and chemical data collection. So once again, I want to thank the different people and agencies that have helped us get this program up and going. I'm going to go ahead and stop recording here in just a moment, and then I'll answer any questions, and we'll talk about next steps as far as getting your practical certification done.